Welcome to a discussion of Le Chatelier's principle. In order to be prepared for this, you will want to have understood equilibrium constant expressions and chemical reactions. Turns out that reactions kind of like equilibrium, that if you have a reaction at equilibrium and you try and disturb it by adding something or taking something away, the reaction will actually shift to regain equilibrium. And Le Chatelier's principle gives us a set of guidelines for which direction the reaction will shift when those changes occur. And we're talking about changes in the concentrations of the reactants or the products, specifically those that impact the equilibrium constant. So you'll recall from your study of equilibrium constant expressions that solids and pure liquids are omitted from the equilibrium constant expression, so making change to a reactant or a product that's a solid or a liquid doesn't really impact equilibrium. Changes in temperature will also come into play here, as will changes in pressure. In general, you can think about this pattern as when you add something to the reaction will shift to the opposite side away from where you've made that addition. And if you take something away from a reaction, the reaction will shift towards the side where you removed something. Let's take a look at an example. We have an exothermic reaction here. Some chlorine reacting with some water to give us hydrochloric acid and oxygen. And I'm noticing that I see water is a pure liquid. And I know that if I was to write the equilibrium constant expression for this reaction, I would leave water out. So that tells me that anything that happens with water when this is at equilibrium won't have an impact on the position of equilibrium. The other substances are gases, so I know they could have an impact. And then I also want to consider what exothermic is telling me. We know that an exothermic reaction is emitting heat. Heat is exiting the system. And so I can think about an exothermic reaction as having heat as a product. If I had an endothermic reaction, then I would think about heat as a reactant, because endothermic reactions have heat or energy coming into the system. So I want to answer these following questions. If I add more chlorine to this system, to this reaction, which direction would equilibrium shift? Well, I check out my chlorine and see that it's on the reactant side. And we know our general rule here is that when I add something, the reaction will shift to the opposite side. So if I've added chlorine, then that means the reaction will shift away from the chlorine and towards the products. So we would say that this would shift towards the products. In question letter B, I have water being removed. Well, we already determined that removing or adding water wouldn't have an impact on the equilibrium position because water is a pure liquid here. So nothing happens in this case. If I increase the pressure, I have to check my moles of gas in the reactants and the products, because you can kind of think about increasing the pressure as you're squeezing down on your system, and equilibrium is going to shift to the side with fewer moles of gas, so fewer moles of things that take up space. I see that in this particular reaction, I have 5 moles of gas here in the products, and I have 2 moles of gas in the reactants. When the pressure is increased, it will shift to the side with fewer moles of gas. In this reaction, that's the reactants. So I would say that in this case, an increase in pressure would cause a shift towards the reactants. If I had equal numbers of moles of gas in the reactants and the products, then changing the pressure wouldn't cause any impact on equilibrium. In letter D, I'm removing some HCl. In this case, I'm taking something away. And we know from our general rules that when we remove something, equilibrium is going to shift towards the side that we remove something from. So since HCl is in the products, and I'm removing it, the equilibrium will shift to make more products, and so it will shift towards the product side. The temperature is raised. I this is where it becomes crucial to have noted where heat is in the reaction. Because if I'm raising the temperature, it's like I'm adding heat. So raising the temperature equals adding heat. Since heat is in the product side for an exothermic reaction, it's like I'm adding more products. So this is like we're adding products. We know from our general rules that if we add something to a system in equilibrium, it will shift to the opposite side. So I'm adding heat. Heat is in the products, and the reaction equilibrium will shift towards the reactant side. You can think about that as it's consuming the excess that I've added and trying to make more of the other side of the reaction to get us back to that ratio of equilibrium. Let's look at another example. In this case, I have some NaHCO3 reacting, well, really decomposing here to make sodium carbonate, carbon dioxide, and water. I see some solids here in my reaction, which tell me these guys are not going to be impacted by changes to the system at equilibrium. And it says the reaction above is endothermic, and that tells me that heat is a reactant. So if I decrease the pressure, I have to check my number of moles of gas. I see that I have 4 moles of gas, 2 moles of gas in the products, and I have 0 moles of gas in the reactants. The pressure is decreasing, so the reaction is going to shift to the side with more moles of gas. And in this case, that's my products. So this will shift to the product side. If some water is added, water is in the products, it's a gas, and we know from our general rules that the equilibrium will shift to the opposite side when something's added. So this will shift towards the reactants. Some NaHCO3 is removed. We don't care what's happening with NaHCO3 because it's a solid, so nothing happens here. The temperature is lowered. By lowering the temperature, I'm removing heat. Heat is present over here in my reactants, so it's like I'm taking heat away. So we're removing heat by lowering the temperature. And we know that systems at equilibrium will shift to make up what I've taken away. So it will shift towards the side where I'm removing something, and in this case that will be the reactants because we're removing heat from the reactants. Some CO2 is removed. We're removing a product, so therefore it will shift towards the products.